All right, for this example, I'm gonna do a little skipping ahead here because the process is the same as the last example and the last question. So the first thing we want to do, first thing we want to do is find our eigenvalues, and we're going to do that by finding the determinant of a minus lambda I and setting it equal to 0. Right? So I've skipped ahead here, and I've determined that the determinant of so this would be 2 minus lambda, negative 4, 3, 4, negative 6 minus lambda, 3, 3, negative 3, and 1. That the determinant of this thing, this is a minus lambda I, comes out to be negative x minus 1, x plus 2 squared, which, look at that. If I set that equal to 0, we have that lambda would equal 1 or negative 2, and this one has a multiplicity of 2. So we already know that it's possible to get a diagonalized matrix for this, right? So I have a multiplicity of 2 here. But what I want to make sure is that when I actually do my vectors there, or when I find my eigenvectors, that I actually have 2 linearly independent vectors that would correspond to the negative 2 eigenvalue. If I don't, then I can't even diagonalize this. So I'm going to focus on that first because that has a multiplicity of 2, and I need to make sure that that's going to give me 2 different eigenvectors. Now, this one is only ever going to give me a single eigenvector. And that's just the way it is because it only has a multiplicity of 1. So that's actually a theorem that's further down the page. We'll explain why. Okay, so here we go. So if I take and I put that in here, I'd have 2 minus negative 2 is 4. 4, 3, negative 4, negative 6 minus negative 2 gives me a negative 2. Nope, negative 4. Jesus. Guys, negative 4. And the last one, 3, 3. And I did it again. I forgot my lambda there. Stupid 3 by 3 matrices. 1 minus negative 2 is negative 3, right? And hopefully what you can see here is that I only get one free variable, right? These two rows are the same, and this one is slightly different, which means that I'm only going to be able to get one free variable in this case. And so therefore I'm only going to have one. This is only going to give me one vector. And that means that I don't have 3 linearly independent. So that means that A is not diagonalizable. Ta-da! Okay, we're getting there. We're getting there. So we're going to determine if this, so in an n by n matrix, if I have n distinct eigenvalues, then it's automatically diagonalizable. So as long as my eigenvalues, I don't have any repeats of eigenvalues, so n distinct of them, that means that they're all unique, no multiplicity is greater than 1, then it's automatically diagonalizable. So here we have a lovely, it's about time that we had another triangular matrix, which means that our diagonal, oh my God, I knew it started with a D. It was just sitting there, just D. Our diagonal contains all of our eigenvalues. So this tells us that our eigenvalues are 5, 0, and negative 2. Now, even though 0 is in there, it's still a number. It's still an eigenvalue. These are all unique. So therefore, it is diagonalizable. Now, this didn't ask us to find the diagonalization. It just asked us, is it diagonalizable? Straight to the point. Yes, it is. Great. If you are feeling real excited, go ahead and find that diagonalization, but you don't have to. So in our first two examples though, right, we had eigenvalues that were not distinct, right? Both of the examples had two different eigenvalues. One was diagonalizable, the other one was not. And so why is that true? So here's our theorem here that's going to kind of help us with this. So the first one says that, so if I have distinct eigenvalues, 1 through p, and I have an n by n matrix. So notice those are different numbers, right? So p and n, no relationship there. For any k value, I believe, what? This seems wrong. I might have totally screwed the pooch on that one. I think my order of my, I did. Oh my God. That didn't make any sense. All right, cross that out. Please make that at 8. 1 is less than or equal to k is less than or equal to p. Ay. So that's just saying that lambda k is somewhere within your counts of how many eigenvalues you have. So the eigenspace of that lambda is less than or equal to the multiplicity of that eigenvalue, right? So so remember the eigenspace is the vectors or the span of the solutions to ax equals 0. That's our eigenspace, is that span. The dimension of that is the number of things that it takes to create a basis for that. So in other words, that's the number of vectors that are in that span. And it's always going to be less than or equal to the multiplicity of k. Now, we didn't finish it here, but there was only one free variable in this equation, which meant that I was only going to get a single vector as my span for the solutions of ax equals 0. So my parametric vector form was only going to give me a single free variable, so a single vector there, which meant that the dimension of that vector space or that eigenspace was 1, whereas the multiplicity of that eigenvalue was 2. In the example in the previous video, we found that we had 2 free variables, which meant that our dimension of our eigenspace for that particular eigenvalue was 2, which is the same as the multiplicity of that. So that's what this first one is saying, is that whatever your multiplicity is on your eigenvalue, your dimension of your eigenspace is always going to be less than or equal to that, right? So if your multiplicity on your eigenvalue is like 6, you could have 6 vectors that make up your eigenspace, or you could have 5, you could have 4, you could have whatever, right? So the matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspaces equals n. So this happens if and only if the characteristic polynomial factors completely into linear factors and the dimension of the eigenspace for each equals the multiplicity. Right? So again, if we look at this example here, in this example, I had a multiplicity of 2 here, and we figured out this was not diagonalizable because I only had a dimension of 1 for this null space, right? And so I had a dimension 1, we've got a dimension 1 here, dimension 1 here, add those together, we only get 2, which is less than 3, right? So that tells us this is not diagonalizable. In the example in the previous video, though, it was diagonalizable because the dimension of our vector space or of our eigenvector space, whatever it is, the null space that came out of our solutions had 2 linearly independent vectors in it, which meant that for the multiplicity of 2 eigenvectors value, we had 2 distinct eigenvectors, and that made it work. All right. Are you confused yet? Yeah. All right, and the last one is that A is diagonalizable, and if B is the basis for the eigenspace corresponding to that eigenvalue, then the total collection of vectors in those sets forms the eigenvector basis for our n, right? So again, if we think about the eigenvalue, we had 3 distinct eigenvectors that made up our eigenvalue, or the last example. It was great. The last 2. We're moving on. Okay. Hopefully that makes sense to you, right? The idea of basis, a basis is just the set that makes up the eigenspace. So it's a set of vectors that are used to create that whole eigenspace. So if we take all of the vectors that create all of our bases, they should all be linearly independent, right? Because each distinct eigenvalue is going to give an eigenvector that is linearly independent from all the other eigenvectors for each distinct eigenvalue. Throwing it all together here. Example, and then we are, did you enjoy that? I did not. No, I did that. Sorry. One more example, and then we are good for the, okay. Thank God. This guy, well, he is a 4x4. So he's a 4x4. He is a 4x4 triangular matrix. And, you know, as they get bigger, they start to be male because, you know, boys bring trouble. Why not? I don't know. That was, all right. Never mind. We're just going to ignore I said that. Okay. That means that I can just look at my diagonal and figure out what my eigenvalues are. So my first eigenvalue is 5. And it turns out that's a repeat. So this has a multiplicity of 2. Now, in order for my matrix to be diagonalizable, that means that when I find the vector space or the eigenspace for this particular eigenvalue, I need to have at least 2. I need to have 2 free variables. So I need 2 free variables in the A minus 5i matrix. And if I don't have 2 free variables, then this is not going to be diagonalizable. Now, the next one, lambda 2, our next eigenvector, value, Jesus Christ, is -3. Again, this has a multiplicity of 2, which means that the A plus 3i vector matrix needs 2 free variables. I was thinking about free, it rhymed with 3. That's what came out. Variables. If that does not happen, if I do not get 2 free variables from each of those 2 matrices, this is not diagonalizable. So let's just go for it. So we already have the hardest part is done here, guys. The hardest part is done, and that is that we already have our eigenvalues, right? We don't have to do our characteristic equation. We don't have to do any factoring. We can just read those suckers off that diagonal. It's beautiful. All right, so let's set up our 2 matrices. So for lambda 1 equaling 5, our matrix, and I'm not going to bother with the augmented part of it because the augmented part of it, the zeros, it doesn't matter what row operations, those zeros are going to stay zeros. So just do your RREF of whatever. So we'd have 0, 0, 0, 0, 0, 0, 0, 0. Hey, look at that. We already have 2 free variables. Didn't even have to try that hard. All right, 1, 4, 3 minus 5, -3 minus 5 is -8. 0, and -1, -2, 0, and -8 again. All right, so we're going to row reduce that. And we get some lovely stuff going on here. We get 1, 4, -8, 0. Give me a 0 here. That would give me a +2. That would give me a -8. That would give me a -8. You with me on that one? Is that okay? And then zeros for days. You all right with that? I think I'm all right with that. Oh, yes, look at that. I think I'm all right with that. Maybe I am. I don't know. Am I all right with that? I'm all right with that, I think. Okay. So this tells me x1 is negative 4x2 plus 8x3. Let's not make that x2. Ooh, oh, no. All right. I'm not going to stop there. Let's not stop there. That was, don't stop me now. I'm having such a good time. All right, so 1, 0. This would be positive 8. This would be negative 8, positive 8, negative 8. Right, so I'm doing row 1 minus 2, row 2. Yep. So oh, this is plus 16, isn't it? Yep. 16. Okay, and then 0, and then I'll divide that, make that a 1, negative 4, negative 4. Oh, okay, that's better. I think that makes. Why not? All right, let's try that. All right. Last but not least, are we good? We're good. We're good, right? So x2 and x3 are our pivots, or our free variables. So x1 is negative 8x2 minus 16x3, 3 and 4. Jesus. And x2 is 4x3 plus 4x4, and then the last two are, so x3 is x3 and x4 is x4. All right, so this is looking good. That means our x matrix is x3 times the matrix times the vector negative 8, 4, 1, 0, and x4 times the vector negative 16, 4, 0, 1. And by definition, these are linearly independent, so we don't have to worry about that. I got 2 of them, which is great. So far we are on a good track here, right? To be able to find our P and our D. So we're going to diagonalize this. Again, we're going to find some P that's made up of the vectors, and we're going to need 4 of them. They got to be linearly independent. And then our D is made up of our, these are our lambdas here. All right, so we already have V1 and V2. So there's V1, there's V2. We're on a roll. So now we just need to go back and do the same thing for lambda 2 being negative 3, and we got to hope again that we're going to end up with 2 free variables. So this one I'm going to let you do on your own. So come back when you have an answer as to whether or not we have 2 free variables and what those 2 and what the 2 vectors would then be that make up our vector basis, or vector eigenspace, well, one of those, makes up a thing. All right, you do it. Come back. Look at that beautifully augmented matrix, which tells us that we have 2 free variables. And it does not matter that the free variables in this one are x3 and x4, because we don't actually give a shit. That has nothing to do with anything. It's just the fact that the vectors we get out need to be linearly independent from the vectors that we got out of the other ones. So this is going to tell us that x1 would be 0. So for our x3 vector, or x3 times 0 would give us x1. X3 times 0 would give us x2 equaling 0, times 1 would give itself equaling itself, and times 0. And then we'd have x4 times, again, 0, 0, 0, 1 this time. And hopefully these look, oh, I don't know, like rows of the the identity 4 matrix, which they're linearly independent by definition. So yay, we have our linear independence. So that means that our P matrix is going to be, and we'll make that be 3, that one be 4. And again, it doesn't matter. We can put those in any order as long as our D matrix also matches up. So our diagonalization here for P, so I'm going to have my negative 8, 4, 1, 0, negative 16, 4, 0, 1, 0, 0, 1, 0, 0, 0, 0, 1. And again, I can put those in any order I like. It does not matter, as long as when I design D, the eigenvalue for this first vector shows up in D. So that would be a 5. This next one had an eigenvalue of 5. This one had an eigenvalue of -3 and -3. And everything else is going to be lovely zeros. All right, there we go. There's our diagonalization. Ta-da! Okay, that's it for the week.